All right, welcome back, everybody. We are doing BTU produced by an anaerobic digester, and you'll notice multicolors on here. That is because as I was building this and making adjustments to my math, and where I maybe overlooked something and needed to erase something, or decided I wanted to throw a different smoke screen in, my other marker did die, and so we thank you for your service. Original marker actually of the channel, it is no longer with us. So I have a new one right here, and that is the darker, more wonderful blue that you see. Okay, enough of that. Let's talk about this math problem. So you're going to be asked on your grades 4 or 5 in California, or your more advanced math in your state, to calculate the amount of energy produced by an anaerobic digester. And how we do that is we measure this energy in something called BTU, otherwise known as British Thermal Unit. You need to expect a very large number for this unit. Just as a case in point, it takes between 60 and 80,000 BTUs to heat a 2,000 square foot house. Okay, so when you're talking about cogeneration plants, like actually running the plant, you're talking millions of BTUs. Okay, and these are typically bigger than the plant that I have given us in this. Those plants are going to be bigger than a 2 MGD plant, but to keep space on the board and math a little easier, I went with a smaller flow plant. If you work in a cogeneration plant, put in the comments below how much flow do you do? What are your BTUs, and how many pounds of gas, or not pounds, cubic feet of gas are you typically producing? So as with most of the math when you get here, there's going to be a lot of smoke screens. Oh, and you know what? Before I jump into that, I put in the title that this is a grade 3 through 5 math problem. So your grade 3, so this is your grade 1, it's a pounds formula. Grade 2 is a volatile solids reduction. So this is going to be a class C level situation, beginner level. Grade 3, which is journey level, is going to be pounds of volatile solids destroyed using these numbers, just one more step, and then potentially cubic feet of gas produced. And then your advanced is going to be figuring out how much your methane is, and then the BTUs with that methane. Okay, so it's just more steps. It's not anything super magical or awful. So let's start breaking this down. We're going to start finding out what we need. So I'm going to just take a real quick glance, knowing that I'm going to have to try to figure out how many pounds of volatile solids are in the digester. And I see that I have an influent TSS and effluent TSS for my clarifier, primary effluent, not plant effluent. Primary effluent is the primary clarifier, okay? TSS, and I have a flow. I can make a pounds formula out of this, and that's how many pounds of total solids are going to the digester, okay? If you go to my organic loading to a digester math problem, you'll see I did this a different way, where there's a pump timer and a total solids percentage, and a percentage of that is volatile. Go check that out, because that is another way this might be pitched to you. When you get to these higher levels, it's a freestyle. You just don't know how they're going to ask you to come up with these numbers, okay? So what I can tell here is that right off the bat, BOD is completely irrelevant to this math problem. That is organic loading to secondary processes is BOD. Organic loading to a digester is in volatile solids. Okay, so I can get rid of BOD. Don't need that. What else can I get rid of on here? Well, I can do a pounds formula with this information. Well, a digester volume is not relevant. This would be relevant if they gave me the loading rate. So if they gave me a gallons, how big the digester was in gallons, or I had to figure it out using the dimensions of a cylinder or a cone or whatever. They would also give me the loading rate of like 0.3 pounds per cubic foot. So that math problem would look like the reverse of the video that you'll see at the end of this video. You can click on and go take a look. You would actually just take the volume and multiply it by your organic loading rate, and that would give you your pounds of volatile solids, if that makes sense. Okay? If you have any questions about that, put it in the comments below. So I know I don't need that. What else don't I need? So I got, okay, volatile solids, 68%. So that's going to be part of my volatile solids reduction math problem. Digester total solids percent leaving. Oh, that's a dewatering math problem. I don't need that, because I've got my digester volatile solids percent leaving. I can do volatile solids reduction with that. I don't need my total solids leaving. Like I said, that's relevant when you're going to a belt press, okay? Cubic feet of gas per pound of volatile solids destroyed, I need that. Percent CO2 and other gases, I need that. BTUs, I need that. Okay, cool. We have what we need for the whole math problem right here. We crossed out the stuff we don't need. So plant flows 2 million gallons a day influent TSS is 215, primary effluent TSS is 115. The difference between the two is 100 milligrams per liter. That's how much settled in the clarifier. Okay, so let's do a quick pounds formula. 2 million gallons times 8.34 times 100 milligrams per liter is 1,668 pounds. Okay, but I'm not worried about how many total solids are in the digester. It's volatile solids, okay? So 68% of the TSS is VSS, volatile suspended solids, okay? Or it could be written several different ways. Just figure out how much of it's volatile. And so now I'm going to take my total pounds, 1,668, and multiply it by 0.68, 68%, is 1,134 pounds of volatile solids. Okay, so I have my pounds of volatile solids being loaded onto the digester, but what I don't know is how many were destroyed. Well, now we're going to do volatile solids reduction. So 68% going in, 0.68, 55% coming out, 0.55, 0.68 minus 0.55 is 0.13. If you are unfamiliar with this math equation, I'll put it in the description below. It's the volatile solids reduction, in minus out divided by in minus in times out. Do the parentheses first down here. So that translates, if I go too fast, look at in my numbers and I'm confusing in how I talk, just look at how I've written it. 0.68 minus 0.55 is 0.13. 0.68 times 0.55 is 0.374. 0.68 minus 0.374 is 0.306. 0.13 divided by 0.306 times 100 is 42%, or 42.4%, depending on, how they're going to present it to you. When you get into that, actually, your BTUs could significantly be different. So if you finish this math problem and you're like a million off, like go back and add or take out the tenth of a decimal place and see how that translates for your math problem. Okay, it'll make a big difference. So now we've got our volatile solids reduction. Simple grade 2 problem. Pounds of volatile solids destroyed. We just put those together. 1,134 times 0.42, 42%, is 476 pounds of volatile solids destroyed. Okay, that's a grade 3 math problem. And let's go back and look at our chart of wonderfulness over here. Okay, here's this one. Cubic feet of gas per pound of volatile solids destroyed is 15. That's a fairly common, that's a pretty standard number from a municipal waste facility. So 476 times 15 is 7,140 cubic feet of gas per pound of volatile solids destroyed. Okay, great. That's also a grade 3 problem. So before we get into the advanced stuff, if you're getting anything out of this, please like, subscribe, pass it to your friends. Let's help folks get certified. So I'm going to get on a soapbox for a second, and I'm going to tell you why I don't like this next step. This is adding a step for the sake of adding a step, and I go pretty easy on the test makers. I think a lot of people give them a bad rap because they feel like they're trying to trick you and all these things, and I don't think they are. They are testing you. But my opinion of this part of the math problem is strong, because nowhere ever would a lab give you the percent of all the other gases and not the methane. I mean, if you're looking for methane, they're just going to tell you the percent methane. So on the test, though, what they like to do is give you everything but methane, because they're trying to make sure that you know that the methane is what actually produces the energy. So they'll do it like this. You're given a percent of CO2 and other gases at, we're going to say for this math problem, is 34%. Or you'll see the CO2 percentage is 30%, other gases is 1%, and then they don't say anything else. Okay, it is up to you to figure out that the methane is the missing part in that 100%. So you just take CO2 and other gases, and that percentage, 100% minus 34%, is 66%. Okay, again, in the real world, they would just tell you that your methane percent is 66%. So 7,140 cubic feet of gas times 0.66 is 4,712 cubic feet of methane, not pounds, cubic feet of methane. I should have written that. Hold on. Let me get in here real quick. Pure methane. Okay, so now we know how much methane is our anaerobic digester is producing. So we're going to come over here and see how many BTUs of pure methane, and it's per standard cubic foot. You'll see it written SCF. That just means cubic feet. Don't let it throw you off. Just SCF is standard cubic foot. Is 992. If they don't list the number here, you should assume it's 1,000. So the textbook BTU of cubic foot of pure methane is 1,000 BTU. Okay, but what they're going to do is instead of that, they're going to give you a plus or minus 8 or 9 or maybe 20, just to make the math more fun, I guess. So BTU is 4,712 cubic feet of pure methane times 992 BTUs per cubic foot gives us 4,674,304 BTUs. And that is how you solve the BTU problem. They might take it a step further and say, well, how many BTUs are being produced per pound of volatile solids destroyed? And all you would do in that situation is then come up here and divide by 476, which I didn't do. But if I tried to do every variation, we'd be here for an hour. Those advanced math problems, like I said in the last video on organic loading, I can't work every single variation of this out. It's up to you to be able to identify what you need in a math problem and carry on. It's like I said, it's like a freestyle. It's like just a conglomeration of all the things you've learned from the 1s through 3, and they're just going to package it any which way they decide the wind is telling them that day. They're going to package it, and you need to be okay with that, because that is, quite honestly, the real world is you need to be able to use different math equations and know when to apply them. That's really, I think, what they're doing. But again, this is silly. I'm just going to say it again. I think that's just so silly. That's such a waste of time for the lab to tell you everything except the actual thing you're trying to figure out for your BTUs. Anyway, or whatever sensors you're using. I don't work in a cogen plant, so I don't monitor methane, but I'm pretty sure it's not figuring out all the other gas and then figuring out it's methane. Okay, I'm ranting and rambling and raving. Again, if you got anything out of this, please pass it to your friends. Like, subscribe. I have a big truck moving by the building, so I'm going to shut my door. On that note, thank you so much. If you have a math problem you want worked out, please let me know. I'm happy to work it out. This should wrap up our digestion math. If you feel like I missed a math problem or you ran into one on your exam, please ask. And as always, if you have anything to add, please put it in the comments below. Have a great day, everybody.